Can you hear me? Hello?
Yes, sir.
Okay, I'm going to start now. Okay, let me start. Okay. Last time I started talking about cluster points. Talked about cluster points. But that is note 6, I think, or maybe note 7. But actually, I didn't finish that more on sequences, this note. More that I have uploaded all the notes there required now. More on sequences. So I will finish this note first and then I'll go to here. More on sequences. First of all, yesterday I proved actually that result. Look, this is very important. That every convergent sequence is bounded. So that if you are asked a question, if a sequence converges or not, first check it is bounded or not. If it is not bounded, then obviously it doesn't converge. Now the thing is that I would like to start a special kind of sequences now, that is monotone sequences. And then I'll go to cluster points, monotone sequences. Okay. Now look, monotone sequences, you have two kinds of things. That is in page 31. I have given definition 1, 2, 3. Okay. First of all, so monotone sequence we have two types, increasing and decreasing. So if it is either decreasing or increasing, then altogether we call it a monotone sequence. Okay, increasing sequence. So you're starting with a sequence. Here, of course, I'm taking real sequence. So that you have the order. In an arbitrary set, if you have sequence, you may not have the order, partial order. Here you have an order. So obviously, this is a real sequence. Okay, now increasing means that xn plus 1 greater than equal to xn for all n belongs to n. First I am defining increasing. Okay, look here, increasing I put greater than equal to. Greater than equal to. It may be strictly greater or equal. But if I write strictly increasing, strictly, look, increasing actually adverb, then it is qualifying this adverb. So this is, so the increasing is adjective. and strictly it is qualifying. This is adverb. Like yesterday I was doing eventually constant. Usually if you have ly, that should be adverb. Here constant actually adjective. As you say constant number, qualify that number. Number is noun. This is adjective. And this is adverb. So strictly at increasing means you have this. This. For all n. Even if 1n it happens xn plus 1 equal to xn, you don't call it strictly increasing. You have to call it increasing just. Look, strictly increasing, already you have an example. When we have defined subsequence, remember that phi, that function I took, okay, that was strictly increasing, okay. So be careful. On subsequence, when you define, then the function phi, that was actually, that will give you a sequence because it is n to n, sequence in n, and it was strictly increasing. So that you should understand increasing, strictly increasing. Most of the time we are done with increasing, but if the special case comes, then you should be careful whether it's strictly increasing or not. Similarly, decreasing, it is the opposite of that. That means you have this. You can define yourself. The xn less than equal to xn for all n. Then it is called decreasing. And strictly decreasing, strictly, is xn plus 1 less than xn. Okay, for all n belongs to n. Okay, examples are easy to find, like, okay, so like if you take xn equal to n, this sequence, it is not only increasing, it is strictly increasing. If I do this, next example, this one, minus n, then it going to opposite, then it will be strictly decreasing. Yes, strictly decreasing. Now, increasing and decreasing together, that we call monotony. Either increasing or decreasing sequence, if you have either increasing or decreasing, then we get a name, common name, that is called monotone. Okay. Usually, if you can do it something for increasing, then you can do it for decreasing and vice versa. Okay, like here I am taking negation, that I will show in the proof also, that you can do it. So that when I say monotone sequence, if you starting with monotone sequence, you can, even if you are not given whether it is increasing or decreasing, you can start. Let us assume that it is increasing. And then after proving that, then you deal with decreasing. That will be the opposite of that. Okay. So that given a monotone sequence, you may not be given whether increasing or decreasing. But in your proof, you will have to assume either increasing or decreasing. And then you can do it. Do it for increasing, for decreasing. The same proof will work, or you will have to take like this. Okay. Right. So that this is monotone. Now the thing is that how monotone sequences behave. It's actually behavior of monotone sequences. Okay. Now look, suppose you are taking increasing sequence. Suppose first you are taking increasing sequence. Again, now look, I am starting. If you just start with monotone, you won't get it. You'll have to ultimately assume, first you'll have to assume either increasing or decreasing. First I'm assuming it is increasing sequence. Okay, that means you are getting this for all n. That means like this, it is increasing. Okay. Now look what is happening. That means this x1, it is less than everybody. That means it is bounded below by x1. So that means xn is bounded below by x1. Okay. This is the information I have always have. In fact, infimum of that, this take the set, we write this infimum of xn over n, all this n. Okay, because set is x1, x2, set A actually is this set corresponding to the sequence. So infimum xn will be x1. Now what about sup? This thing. Now look, this is the question. Here, this sequence, it was strictly increasing. It was bounded below by 1, but it was not bounded above. It was not bounded above. So that on the other hand, of course, you can have monotone increasing sequence which is bounded above. Okay. How to give that? So that xn equal to n if you take, then xn is increasing and not bounded above. An increasing sequence always bounded below. Okay. Now I want to have a sequence which is another sequence I need, which is increasing and bounded above.
Minus 1 by n.
Minus 1 by n, that is fine. Yes. How we are getting 1 by n. This is actually, now look at about this. This is decreasing. This is okay. This is decreasing. Okay. This is bounded. Bounded means bounded above and below. Look, a decreasing sequence, it will be bounded above by 1. So it is bounded above by 1 and bounded below by 0.
0.
So it is 1 by n. Elements are in this. Actually, infimum will come. Sorry, write that. Infimum of 1 by n, n is 0. So if I took minus 1 by n, this sequence, this will be increased because this is decreasing, so this is increasing. There it was lying in between 0 and 1. So here it will be lying in between minus 1 and 0, right?
0.
It says 0
Yes, sir.
open.
Open. I am saying lying, lying in. That is not the language is wrong. You are
Okay,
right,
sir.
it is open.
Yes, sir.
But I am saying lying inside. I am just only concerned whether it is bounded or not. Fine. 0 will be here infimum, here is sup of, here sup of minus 1 by n, that will be 0.
0.
Now look at the example. The theorem I am going to give you, that will be simple. Look. First increasing, decreasing you can forget. Decreasing just you take a minus and that you can do it. Or you can use the similar arguments. Now look, it is increasing, okay? Then actually that I have not talked about extended real line. That means sup of xn, you can think of this, that it is unbounded infinity. That I need to explain that what is infinity. Okay. And whereas if it is not bounded above, but whereas if it is bounded above, then look, this 1 by minus 1 by n, it is converging to 0.
0.
Right? This is converging to 0. But this 0 is same as this. Okay, so that if it is bounded above, let me first handle bounded above. Bounded up, not above, that I will consider later. Bounded above, that means here you have an idea. If it is bounded above, it will converge to its supremum.
Supremum.
So that's the result I have done basically. That's the theorem in the page 31. Page 31 you look. Here the theorem is that every I did it for monotone bounded, you want to know either decreasing or increasing. First you do it. Every increasing sequence bounded above. Here everything is real sequence. Bounded above. I'm doing this. Which is bounded above is convergent. Look, you can read from the note. So I'm not going to write everything. So, but I can explain that. So suppose this is your xn sequence and it is increasing. This is the notation we use. This means upper arrow. That means it is increasing. And it is bounded above. That means this. For all there exists m real number. To m for all n, because I am assuming bounded above. I am just using the definition since it is bounded above. So particularly sup xn, particularly xn less than equal to sup xn. Okay, we call it itself m. Okay, there is, suppose we call it, say, okay, I'm just, it may be a different m, but I am this sup xn, I'm calling it m. Okay, if you want, you can write m prime, and here you call m. Okay. Now look, I gave you a property of sup, that term. Now look what is happening. This is your m sup. Okay. What I need to prove that you take any neighborhood of, here I have taken m minus epsilon, to take m minus delta, m minus epsilon, m plus epsilon should contain almost all the members of the sequence. That means eventually the sequence should be in this neighborhood of m, right? Okay. So I don't need to bother about m plus epsilon because all the members of the sequence less than m. So you can write, but you don't need to bother about it. But look here, this is your m plus m minus epsilon. Okay. Now look at the property of that. For any epsilon, since this is less than sup, so there will exist a member xn naught, right? This n naught will depend on epsilon. There will exist a member xn naught. Now what will happen about the member xn where n greater than equal to n naught? Look, if n greater than equal to n naught, then it is increasing given. That means xn greater than equal to xn naught. At the same time, xn is less than equal to m. So that xn will be lie in between this, right? Got it? Have you got
Yes,
it?
sir.
Yes, sir.
Yes.
Yes, sir.
So everything will be here. That means that I have got already. That in this neighborhood, after n naught, every member of the sequence is there. Xn is always here. That means you get one member by using the definition of the supremum, and then since it is increasing, all these members greater than xn naught will be there. So it's done. This is the proof, done. Got it? So that is the trick. Okay. Now look, this is for increasing sequence I did. For infimum, you can use you can do it two ways for the decreasing sequence. Look here, suppose you have in xn now decreasing, so that you call it decreasing bounded below. Decreasing, suppose this is decreasing and bounded below, because when you have decreasing, it is bounded above by x1. Okay, so here your candidate will be in xn. It will converge to infection. Now look again the idea. Here it is the mirror image. Suppose infection is m. So we are taking m plus epsilon, here m minus epsilon. Look, everybody is greater than equal to this small m, so that you don't need to bother about this part of the interval, left side of the interval. Here right side of the interval you didn't need to bother on this. Here left side. So here by the definition of infimum there will exist a member xn naught, but it is decreasing. That means everybody else after that it will be here. Okay, and that exactly you get, so that you can imitate the proof. Okay, or else you could do it. Okay, that exactly. Now look, I could say xn is decreasing, suppose. And bounded below. Okay, so that minus xn is increasing and bounded above. But here you will need a result that you need to prove. So that by previous result what I proved, that minus xn converges to sup of, right? Okay, so that is easy to prove for by using triangle inequality. If you multiply by negation, then xn converges to minus sup of minus xn to n. Here, look, in the end of the proof, page 31, that I showed, you need to prove this. Look, this minus is there. This is a result. This is given in as an exercise in Alipran's working set. The minus
in infimum of x.
That this minus it will be outside, but when sup and inf you change, so it is goes to infection. It is easy to remember that in sup xn, if you have minus here, if you want to take the minus out, then it you will have to change it to infimum. समझ गया क्या बोल रहा हूँ?
Yes, sir.
Yes,
That
sir.
means minus
Yes, sir.
sign and minus sup in, they are sort of, and inf, they are sort of dual. If from swap to in, sup to inf, or inf to sup you want to go, make sure that you take care of the minus sign. Look, from this result I can also get inf minus xn. Just use this result. It's the dual of this result. Okay, so this is minus inf minus xn, and by this result this is minus of that, so this is minus sup xn. Got it? You need to prove only one result, but actually you'll get two results. These are called mathematics called the dual result. Dual result means, like here I'm getting a dual result, that increasing sequence, if it is bounded above, it converges to supremum. If you have a decreasing sequence bounded below, it converges to infimum. So these two are dual results, because you need to prove one result. Other result you can do it from the, either you can get the proof of the previous result, or you can get by using that result. Look, you have two proofs. One, you are using the result itself. Another one, you are using the proof. Okay, so different is that either you use the proof or use the result. So my suggestion is that read it this carefully again, that the result on that page 31. Okay, so that every monotone sequence, if it is bounded, that means bounded, because monotone sequence is always bounded in one direction. It is bounded, it has to be bounded in other direction, and it converges. So the monotone sequence, that will behaves very well. If monotone sequence bounded, monotone plus bounded implies convergent. Okay. So it is very nice. That means if it is monotone sequence, if it is bounded, it is increase. If it is an increasing sequence, if it is bounded above, then it converges to its supremum. And if you have a decreasing sequence bounded below, then it converges to infimum. So behavior is well known. Now what happens? Now the question is monotone and unbounded. That is the question. Look, here also sequence behaves very well. That we will see that. Here we talk about extended real line. Let me now explain that. Extended real line. Notation is R star. Some people use it is not standard R bar also. They use it. Okay, so you should look at that book. Depending on the book, it depends. In this book, Ali Francis Berkinsa, they have used R star. Now look, R star. Here, be careful about this. They're adding two notation. Okay. Anyway, they are using this notation plus infinity. I am just using this notation infinity because it will definitely look different from that. Now look, first thing, extended real line we are taking. First thing, these two, again I'm telling you, first thing you should remember that they are not numbers. Okay, they are not numbers. Real line, everybody is a number. Here they are not numbers. If it is not number, then what is there? Look, real line, I could think of as a set, everybody is a point. Okay, like if you have a set X and elements are here the points, elements. So here I am thinking these real numbers, each real number has an element. With this set R, I am adding two more points. And what are those points? Here, so that these 2 points actually are notion or idea. What is that? Here, I said how with the partial order, because I have a partial order here. How will I link with that? Here, this thing is this. That means it says it's a notion such that it doesn't matter how small a number you choose, it is always on the left of this, left of that number. That means you choose any number m, it doesn't matter how small, that is particularly how big negative numbers, okay, big negative numbers. So this is always on the left. We not less than equal to real number n, strictly less than. That means this is always on the left. That I am defining. The notion, that is I am defining. Again, that's why I'm telling they are not numbers. They are not numbers. They are notions. They are ideas. They are concepts. Okay. Similarly, for the infinity, it doesn't matter how big number you choose m, big, large number, positive numbers, still it will be this. That means it will be on the right of this. That means here if you have 0 real line, it doesn't matter how much on the right you go. Okay, infinity is a concept which will be always on the right of that. That means infinity, even if you move, doesn't matter how fast, how big, you won't be able to touch it. That keep your mind. You won't be able to touch it. In the limit process in the high school, you have not learned the limit definition correctly. Most of you can see that limit. That's why look here, when you have in high school you did limit x, limit x tends to 3. I'm just giving an example. How did you do it? X tends to 3, but it is never equal to 3. That you use that concept. That's why you could cancel x minus 3, x plus 3, and then you took that it is 6. That is what you use. X tends to 3, but x is never equal to 3. Okay. Similarly, for infinity, going large like n, if I take numbers xn, it will go to infinity. but it will never touch infinity, because whenever you pick up any number, it is still a real number. It is not infinity. So infinity is a concept. It's a sort of limit process in that, but it is not a number. You will never be able to touch it. Similarly for minus infinity, minus n, if you take, it is going to minus infinity, but you will never be able to touch it. That means it doesn't matter how big n you choose, that means how small minus n becomes, still it won't be equal to minus infinity. So it is in the limit process. So this is called, but still then you may ask why we need it. Because it needs, because we can explain the things, we can convey the things very nice way, briefly. We don't need to talk a lot of things. Like here, when I say, that means what I say, if it is a monotone sequence, now look, if you have a monotone sequence, if it is bounded up, not bounded above, not bounded above, okay, that means xn, you can say xn actually will be have to go to infinity. Okay, but then what will be sup of xn? But you can say actually what will be the meaning of this if the sequence goes to infinity? I can give you a precise definition that I have given, I think. Okay, precise definition is this. Look, is simply this. I say xm tends to infinity. I can give the definition that, look what I'm saying. If given m greater than 0, it is not epsilon, m greater than 0, it doesn't have matter how large, however large, you can write for your understanding, though you don't need to, you are not required to write it. However large, there exists n naught such that xn greater than m for all n greater than equal to n naught. Okay, this is the meaning of xn tends to infinity. You give me any large number, I can always find n naught such that this, like xn equal to n, it happens. Okay, you give me any number, you choose a natural number, first n naught greater than m. First, suppose you give me any number, so choose, m may not be an integer, so choose n naught belongs to n natural number such that n naught greater than m. That I can do. Why I can do it? You need that problem. That came from well ordering principle. Actually, not that. I think idea of the supremum. That set of naturals is not bounded above. Set of naturals is not bounded up. If you have m's, make sure that if it is not integer, there exists integer n naught such that I will have this. That is, it will be in here. We should be careful. If it is equal here, obviously it is not equal here. It means either this. It will. That you can always find. That if you have a large number, doesn't matter how large, I can always find a natural number such that m will be this. Okay. If you can't find it, then you know what will happen. Okay. What will happen? For any n naught, you are not getting into that. That means what will happen? You can, so you will get a contradiction. So that this is the definition. There exists such that I have this. Similarly, if you take x naught, n naught minus infinity, that means given, I don't need that. Given and if they don't come together. Given means you have if m greater than 0. And given mean also that any. Now here given, you can take that m less than 0. Okay. There exists n naught such that xn less than m for all n greater than equal to n naught. Okay. Now, what is your choice? If it is, now look, that already said that monotone sequence, if it is unbounded, suppose monotone plus unbounded, first you see. But unbounded means happen what? Depends on increasing. If it is increasing, then again you'll have to look to possibilities. Monotone means either increasing or decreasing. That means if it is increasing, then it is not bounded above. Okay. What are you doing? Huh? I think somebody is in home, somebody is calling. Xn and xn in decreasing. If it is decreasing, then not bounded below. Got it? If you have this unbounded, that means you'll have to see that what is monotone. If it is increasing, then it is bounded below by x1. So it is not bounded above because of this. Okay. And if it is decreasing, it is bounded above by x1. So that because of unbounded, it won't be bounded below. So in this case, where first case, x1, xn will go to, actually what I defined, xn will go to infinity. There xn will go to minus infinity.
Minus infinity.
Yes. But now look, when you use this, there is a difference. You can say they are not converging in the real line. They are converging in the extended real line. So that when you talk about convergence, it should be very clear. Whether you are converging it in R, that's why some people in BSc, I think you have got it, they are divergent, these things, because they are only talking about real line. So that if you talk about convergence of a monotone sequence, you should be clear whether it is converging to a real number or it is converging to infinity or minus infinity. Understand? Okay, they should be clear about it. That I said that. Okay. So extended real line, I think page 33, all these examples that I have discussed actually. Okay.
Sir?
That's page 33. Already basically I have discussed basically similar things. So you can read that. Okay. Right. So that now you know the at least behavior of monotone sequence. First of all, a monotone sequence, it will be bounded or not bounded. If it is monotone, now look, then let me write. So monotone sequence, it will be two things. It is bounded, it is unbounded. And in this case, it will come two things. I'm splitting, either increasing or decreasing. Actually, I should have split here, increasing, decreasing. It is a monotone bounded sequence, increasing, decreasing. So this is bounded. So this will go to here. If you take xn, this will go to xn will go to sup of xn, and here it will go to
Infimum of x.
xn. Look, another thing I forgot to tell you. If it is unbounded, then again increasing, decreasing. Then xn goes to infinity. Here xn goes to minus infinity. Now
Minus
look,
infinity.
this infinity when it is increasing, but unbounded above, that I can also think of sup of xn. Okay. If it is an increasing sequence, if it is not bounded above, that means that I can think of also sup. Okay. That I can think of sup, and this I can think of this minus infinity, I can think of n, because this is the only idea, notion that which will be less than equal to each member here. Understand? Nobody else will play that role. Similarly, here, this idea, this notion, infinity, will be greater than each xn. Nobody else will play that role. So I can call it in this case, this is sup. So and if I do that, then look, here xn is going to sup xn, here also sup xn, if it is unbounded. Similarly, if it is bounded, it is inf. If it is unbounded, still it is inf. That means I can always say that xn, depending on that, limit xn is sup xn if xn is increasing, this notation, whereas limit xn is inf xn, okay, if xn is decreasing. I can, in one notation I can express everything, okay. But again, you should be careful. Given the situation, you know that where it is converging. समझ गया? ठीक है? So that you know the behavior of the monotone sequence now well. So that when I am going to deal with the sequence, if I want to know the behavior, then basically I need to look at non-monotone sequence. Non-monotone sequence. Okay. Look, monotone sequence often comes into the picture and it plays big role. In major theory, next semester we'll be doing, there is one thing that is famous theorem, monotone convergence theorem. It's called MCT. Look here, the last page of that, I am talking about linear spaces of real sequences that I talk about. In major theory, basically it depends on three theorems. This is one monotone convergence theorem and one Fatu's lemma. It is actually a theorem, not a lemma. And Lebesgue's pronunciation is Lebesgue. So Lebesgue's dominated convergence theorem. These all deal with the sequence of functions. That's why I'm going to write, I have written a page in 34 about the functions in the dominated convergence theorem. LDCT. LDCT. Okay, so that these are all deals with the sequence of functions, and the whole major theory basically depends on this thing. If you understand these three results, you should have a grip over major theory. Okay. Now look here, name is monotone. It's there. Okay. Right. Lebesgue's dominated convergence theory. Right now I was talking about SUP. They are calling it SUP of Fnx, inf of Fnx. That these are the functions coming. Okay. So the sequence of functions comes. That eventually I will teach you that sequence of functions. Right now, so non-monotone sequence, and that the major theory, in fact, if after your first semester is over, there will be a gap of 1 month if you want. Robert Bartle, this book, I think it's a small book, but it's a very good book. Elements of Major Theory. His second edition is Elements of Major Theory and Integration. It doesn't matter whichever edition you get. Elements of Major Theory. May find in the net. It's a short book. Anyway, Bartle was one of the leading major theorists of the last century. Okay. Bartle was known for his works in major theory and integration. Look, if you ask me, I'm just going a little bit away from this course, that if you ask why we need to do measure theory. In Bartle's book, if you find first chapter, he's calling it as introduction. That why we should do measure. Look, measure actually is related to integration. Okay, why you should do measure theory? Measure theory's main contribution is the integration of a large class of functions, not necessarily defined on the real number line, not necessarily like Riemann integration. Riemann integration, let me tell you in one word, is highly inadequate. Ultimately, it doesn't serve the purpose. So ultimately, it has to be replaced by Lebesgue integration. This will give you this, the idea of the Lebesgue integration. Okay, so that, but here the sequence of functions come. How sequence of functions will come? Look, I'm just giving an example that on this 0, 1 interval, for each n, I'm defining fn x into x to the power, that is fn x equal to x to the power n. Got it? Look, this is a real valued function, but here instead of, here I am having this sequence of functions. Okay. Then say the sequence of functions. I said a sequence is usually defined as a course. Don't confuse with this, that with this and this. Okay.
Yes, sir.
A set x. Then he said, but what will be this range sequence of functions? Okay, that means space. That means this set x. What is x for this sequence? Did you get my point? What is this x for this sequence? They are not
fx.
simply these points. Okay, that means I am not taking a sequence of points only. I am taking a sequence of functions. That means you need to have the collection. You need to consider the collection of functions. That exactly I did in page 34. Look, here I am giving you special situation. It can be defined for any set. Look, here I said, here everything will work inside R, the real line. So the suppose I take a function now. X is any set. Okay. First you see that the function. Don't worry about, I have not given any metric in that. Don't worry about anything continuity, just a function. So this is called a real valued function. आज तो लगता है that cluster points I won't be able to teach you anyway. I think real valued function. Okay. Now look, if you have a real valued function, suppose you have another real valued function. So I can define their addition, f plus g. You did it in B.sc for when x is r or x is an interval. So f plus gx, you define fx plus gx. Look, this I'm using same notation, but this is addition of two functions. But here it is addition of two real numbers. Look, fx given x here, fx is a real number. Similarly, gx is a real number. So it is addition of two real numbers. Okay, it is usual addition of two real numbers. Look, in mathematics often use the same notation for different purposes, because if each time, if I use a different notation, then ultimately you will have more notations than mathematics. Understand? You will have millions of notations. This you should understand. This is not the usual addition of real numbers. This is what you did in B.Sc linear algebra. This is the addition. I am defining. This is a defined. I am defining. Defined. Here it is addition of two functions. Similarly, if I take alpha, a real number, and f is here, then alpha f I defined. That is product by a scalar. Alpha is also called a scalar. Then you define alpha. Actually, it's itself the putting the bracket. Together is a function. Alpha I'm defining. Look, this is well defined because fx is a real number, alpha is a real number, so this is a real number. So here this is called a scalar multiplication. Because any real number also is called a scalar here. Scalar multiplication. So with these two, this is the definition again. So with this definition of, it's called the addition of function, usually vector addition. Now, if you take all functions, now suppose I write fx, write the set of all. Here I have taken sequences on that will come. Okay. I'm coming that. I will reconcile with what I wrote in page 34. Set of all real valued functions on x. Okay. Here I have already defined addition and scalar multiplication with two functions and scalar multiplication. I'm writing short, it is multiplication, whole thing. Alpha f. With these two operations, you can check that fx is a vector space. Vector space is also called a linear space. Is a vector space, also called linear space. Over it's called the real vector space. Look how I defined addition here. It was defined pointwise, or you can call component wise. Look, how I defined f plus gx. I defined fx plus gx. This means each point you are defining. It is called defined pointwise. Okay, I defined. Similarly, here also I defined pointwise. I defined this pointwise. Look, function. Another thing in B.Sc, I don't know that in high school this fx. Make sure that you understand. Fx is not a function. Fx is the value of the function at x. F is the function. F and fx, they are different. In old books and many teachers still they use the notation for function. Fx is not a function. It is the value of the function f at x, whereas f is the function. Okay, right? So with this, fx is a vector space, linear space over R. Now look, if I take particularly x equal to n, I said any function on real valued function on n means what? It's a
Sequence.
real sequence, right? So that special case I'm taking x equal to n. Then sequence is a function. That means what I did fx. Look, if I take fx now x equal to n, if I take that, it will mean what? The vector space of all real sequences, right?
Yes, sir.
Yes, sir.
Okay, but then what will be the addition? Look, xn is nothing but fn. Got it? So that if I have a plus g, two function sequences, okay, so xn you call fn and yn you call gn, another sequence. Yn, that is another sequence. The f plus gn, this is fn plus gn. Fn is xn plus gn. And so look, that means what I got? Addition of two sequences, component wise, point wise, that xn plus yn. That means if you want to have, just you want to go straight for the sequence, if I xn y equal to yn, x is a sequence, understand, xn, y is a sequence y, then x plus y is actually this, is nth element is xn plus y. That means you have this, point wise you are adding, or some people call it coordinate wise. This means it is continuing. Similarly, look what I am getting, this. Look. In here I am getting component wise, coordinate wise addition. Okay? Similarly, if you have alpha xn, look, alpha x, that is alpha don't forget fn, actually xn is nothing but fn, it's value of a function at n. So this I am getting alpha x1 of 3 dot and alpha xn. Okay? So when you are having just sequences, not, but sequences is a special case of functions that I already explained. But now if you go for sequence, addition of two sequences you define this way, and scalar multiple of sequence you define this way. Okay, this way you will get what? Set of all sequences, that I called it, just gave the name because sequence A stands for this. I have taken this thing. Okay, but later on you see that has got another notation. This I gave the set of all real sequences. Okay, and this I got a vector space, linear space over. Now look, if I took all complex sequence, okay, then it will be a vector space over C. Understand? Okay. So here
Yes,
I
sir.
am just doing real analysis, so I am taking real sequences. Got it? So that this, I said, it is a vector space. Okay. Now you see that I have given example this thing. Now you know in linear algebra subspace SC. Suppose this is the sequence xn. Those sequence, real sequence, such that xn is convergent. Look here, I am not taking all the sequences. I am taking only the convergent sequences. You can prove that that is a subspace of vector subspace of C of S.
Yes.
That is clear because you need to prove if sum of two convergent sequences is a convergent sequence and scalar multiple of a convergent sequence is again convergent. That you all need to prove because it is closed with respect to the operations addition and scalar multiplication. That I said that. Similarly, look here I have taken all sequences. Here I have given one example convergent. Another example I could take is the bounded sequence. Xn, you are taking the sequence such that Xn is bounded. Okay, I could take many things. Xn is bounded. So this will be again sum of two bounded sequence will be bounded, scalar multiple of a bounded sequence will be again bounded. So that this is also a subspace. So this will be also subspace, so that you are getting this, this, and every convergent sequence is bounded. So this. Okay. Now since I am working on the real line, I can look at those sequences, convergent sequences which converge to 0, like 1 by n, minus 1 by n. This converges to 0. Okay. So take the sequences, all convergent sequences which converge to 0. You will see some of these two sequences will also converge to 0, and scalar multiple of such a sequence will also converge to 0. So that if you take S0, S0 is those. Again, it will be a linear subspace, vector subspace. It is converging to 0. So you are getting all these things. Look here, what I have taken all sequences, then I have taken bounded sequences, then I have taken convergent sequences, then I have taken convergent sequences where the sequences converge to 0. Okay, here why I have done it, let me tell you that. Here, these things in function analysis, later on also in the real analysis, this is called L infinity. This is called small c. This is called C0. These are called sequence spaces. In functional analysis, there is one area people work that is called the sequence spaces. Okay, so these have got the special names and that. Okay, so L infinity C C0. Okay, so that's why I am saying this is a part of function analysis basically. So anyway, I think I will. Where is your next class on Friday? Huh? I think it is on Friday, right?
Yes.
So I'll take the next class on Friday, but make sure that you read page 34 specially. Try to understand, read page 34 of my note and relate it to your knowledge on vector space, what you did in high school. Okay, sorry, in your undergraduate, the vector space. Okay. Look, in function analysis, let me tell you that. Why some students find it difficult. Function analysis, you need to know basic function analysis. If I go, is a core course for basic function analysis. You need to know 3 areas: real analysis. In particular, you need to know metric space. That I will start. If not next week after that, I will start metric space. You need linear algebra, that is knowledge of that vector space. Linear algebra. Linear algebra, look, matrix theory is different from linear algebra. Don't confuse matrix theory. You need linear algebra means you need knowledge of vector spaces, particularly infinite dimensional vector spaces. And if you go for nicer examples than that, you need to know measure theory. In fact, function analysis was born in 2 directions. One direction, it came from measure theory. Measure theory came before function analysis. Okay, function analysis was born in 2 directions, and one direction was measure theory. Okay, so that without good knowledge of measure theory, we will never have good knowledge of function analysis. But the thing is that, and here I said basic, when you go for advanced function analysis, then metric space will have to be substituted by topological spaces. General topological space that will be doing in the next semester. The thing is that students find it Here it is all interactions. It is not one area. It will have the interactions on in all these areas between among them. Okay. My problem is that many students fail in catching up with these interactions. It is not one subject. So unless you have the knowledge, basic knowledge of all these three areas, you will have problem in functionalities. Okay, that's why right now I'll say I don't know how much you linear algebra you did, but I think you are taking a course in linear algebra right now, right? Hello.
Yes, sir.
Yes, sir.
Who is teaching that course?
Puneet Sharma, sir.
Then so he's teaching matrix theory, I think.
No,
Let
sir.
me tell you.
Vector spaces. He started
But
vector
whatever vector
spaces.
space he teaches, make sure that you read it very well. You will need that. And infinite dimensional. Let me tell you that. In linear algebra, usually we deal with finite dimensional vector spaces. Okay. Usually we do not talk about infinite dimensional vector spaces. But function analysis, we need to talk about infinite dimensional vector spaces. From that viewpoint, linear algebra is called finite dimensional function analysis. But point is that there you'll have to deal with mainly infinite dimensional vector spaces. So that if you are studying some vector spaces, make sure that where you are using infinite dimensional function. Look, right now I said this sequences S, sequence space. Okay, all this I talked about that SC, SB, S0, S, all these are infinite dimensional. They do not have finite dimension. All these are infinite dimension. They will have a basis, but the basis will have to be infinite. Okay, all these things not finite dimensional, so they are not part of linear algebra. They are part of linear spaces. They are not part of linear algebra. Okay, make sure you read it and read some linear space. Here I should tell you one book, good book. Okay, what is the name of that? Pierre Helmholtz. So this is finite dimensional, but I think in the library you'll find, I think you'll find in the name, finite dimensional vector spaces. It's a very good book. I think about Helmholtz I talked one time. This book. You should look at that. Okay? Okay? See you on Friday. Bye.
Thank you, sir.
Okay, sir. Thank you.
Thank you, sir.